All right, so we just gave some motivating remarks about what the cross product is yesterday. So now solidify that a little bit by first giving a precise definition. So let's suppose that vector B has three components, V1, V2, and V3. And vector W, likewise, is three-dimensional. Vectors in R3. Then the cross product we denote V cross W is defined as follows. V cross W is given by the determinant of the following 3x3 matrix. I hat, J hat, K hat, V1, V2, V3, W1, W2, W3. Another thing we did yesterday was just talk about what a determinant is. Slightly. Oh, it seems like I'm frozen on Zoom. There we go. That's better. Right. So we talked about how to compute a determinant for a 2x2 matrix and gave some hand-waving justification of what a determinant actually is in terms of how it behaves, something like a measurement of a matrix or some characterization of a matrix is given by its determinant. How do we take a determinant of a 3x3 matrix? Well, taking a determinant of an arbitrary n by n matrix is an inductive process, by which I mean it's built up. If I want to take a determinant of an n by n matrix, I have to take n minus 1 by n minus 1 determinants. And then to take an n minus 1 by n minus 1 determinant, I have to take n minus 1, n minus 2 by n minus 2 determinants, and so on and so forth until I go all the way down to 2 by 2. Okay, so in other words, to calculate this 3 by 3 determinant, I'm going to have to calculate 3 2 by 2 determinants. And the 2 by 2 determinant formula is just something you have to memorize. AD minus BC. Okay. So let's discuss how we actually calculate this 3 by 3 determinant. Here's what we do. We start at the top row of the matrix, and we first look at the first entry of the top row. Okay, so this is equal to this vector I hat times the determinant of the following 2 by 2 matrix. What I do is I eliminate the first column and the first row. I pretend like they're not there. And that leaves me with just this 2 by 2 matrix, B2, B3, W2, W3. Okay? B2, B3, W2, W3. Okay? Now I stay in the top row and I move down to the second entry of the top row. And this time I subtract times the following 2 by 2 determinant. I do the same thing here. I eliminate the column that this entry is in, this J hat, and the row. And I'm left with a 2 by 2 matrix, right? The entries of which are V1, V3, W1, W3. Okay. Plus, we put an equal sign here just so we know that this is formula for this. Plus the final entry of the top row, K hat, times the determinant that we get by deleting the first row and the third column. V1, V2, W1, W3. V1, V2, W1, W3. Just for completeness sake, let me remind you what each of these 2 by 2 determinants calculated out is. So the determinant of this 2 by 2 is V2 times W3 minus V3 times W2 minus J hat. Remember, as we move along the entries of the first row, the signs alternate in the calculation of the determinant. Positive, negative, positive. Okay, so minus J hat, this 2 by 2 determinant is V1 W3 minus V3 W1 plus K hat times this 2 by 2 determinant, V1 W2 minus V2 W1. Okay, so you're more than welcome to try to memorize this formula. I think there's a lot of opportunity for error there. I think it's much easier to just remember how to take the determinant of a 3 by 3 matrix and just do it each time. Right? Here you have to pay attention to all the indices and make sure that things go right. There's a lot of opportunity to mix up the signs, right? Which actually will hurt you a lot in trying to interpret the cross product correctly. So really, it's this equality that you want to remember, that you take the entries in the first row, alternate the sign, and compute the relevant 2 by 2 determinants. Okay, but you can do whatever you want. If you have no problem memorizing this, that's fine. Okay, so one teensy side note here. Typically, when we talk about matrices, all their entries have to be the same kind of thing, right? Talk about a matrix as being an array of numbers. Notice that's not the case here. Our top row are vectors. and our bottom two rows comprise of numbers. This is kind of an abusive notation, but we allow this because we want our output to be a vector, right? So I, j, and k are all three-dimensional vectors, and each of these determinants is just a scalar, right? This is kind of the standard way to write a vector in the standard basis. I, j, and k added together times some scalars, right? So for those of you who have any familiarity with linear algebra, you might find this kind of disagreeable that we have vectors in the first row, but it's just a useful abusive notation that everybody uses. So I apologize for that. Not that it's my fault. Okay, so let's do some examples. Let us show that I hat times j hat, I'm sorry, cross j hat is equal to k hat. Okay, so now this might seem doubly confusing because not only do we have I, j, and k as entries in our matrix, but now we will find the other entries of our matrix from the vectors I and j themselves. Okay, so let's just apply the definition. Straightforward. Okay, so I hat cross j hat is equal to the determinant of the matrix I hat, j hat, k hat. Then for my second row, I put the entries of I in. What are the entries of I? Yeah. 1, 0, 0. Yeah, 1, 0, 0. Okay, and then for my third row, I put in the entries of j. What are the entries of j? Yeah, good. Okay. So move up to the next board. We apply our formula. We take our first entry, I hat, and we take the determinant of this 2 by 2. What is the determinant of this? 0, right? 0 times 0 minus 0 times 1. Just 0. Minus j hat times. Okay, so now I want to consider the matrix 1, 0, 0, 0. What's the determinant of that matrix? 0. Good. Plus k hat times the determinant of this matrix. And the determinant of this is 1, right? 1 times 1 is 1 minus 0 times 0. Okay. Not so hard. Also, this gives some credence to what I was saying yesterday. When you take the cross product of two vectors in R3, you get a vector which is orthogonal to both of them. If I, j, and k are the standard basis vectors, they look like this. Right? Here's k hat, I hat, j hat. They're all mutually orthogonal, right? Yeah.
They said when you take a cross product of two vectors in R3, you're going to always produce orthogonal.
Yeah, that's right. That's right. And we'll emphasize that again and again. In fact, that's one of the main reasons we're interested in the cross product, because it has this orthogonality property. Okay, so this matches claim that in general, U cross V is normal to both U and V. Okay, this is just one example that reinforces this claim. Okay? K is orthogonal to both I and J. I'll ask you to check on your own that K hat times K hat equal to I hat, and K hat times I hat is equal to J hat. Similar computation as to the one we just did, but a nice relationship between these things nonetheless. Okay, so now I want to talk about, remember when we discussed the dot product, we said that it encodes certain geometric information about the vectors that you're taking the dot product with, right? Namely, with a little bit of computation, we can calculate the angle that two vectors meet, the angle between two vectors, using the dot product. Okay? In a very similar fashion, the cross product also secretly contains some geometric information. Okay, so let's discuss that. Okay, so again, let's take U and V, vectors in R3. Then we know, sorry, should say non-parallel. We'll see why in a moment. Then we know U and V form a parallelogram. Here's a schematic diagram. W. U. The angle between them. Remember, we discussed this very early on. Two vectors, which are non-parallel in any dimensional space, form a plane, right? And in that plane, depending on the angle between them, we get a parallelogram simply by translating V along U. Or I'm sorry, I said W. This is V. Simply translating V along U, I get the other parallel side, and then I can translate U along V. Get another parallel side. Okay. Parallelogram lies in a plane spanned by U and V. So here's the question. Does anybody remember how to calculate the area of a parallelogram? Yeah, that's one way to do it. But there is a formula that just uses the information given here. Yes.
Just base times height.
Base times height. Yes. What is the height of a parallelogram. Yeah, exactly. You drop a perpendicular here. Right? This is the height of the parallelogram. So area of parallelogram is equal to sorry, so this is the base of the parallelogram, the long leg, yeah, is base times height. Now, how can we quantify the base in terms of the vectors u and v? Yeah, well, not quite. The orthogonal projection would just be here. You're projecting v onto u. I asked the question in a misleading way. This is just the magnitude of u, right? The length of this vector u. Okay, so that's the base. Now, how about the height? How do we calculate this distance? Yeah. Yeah, exactly. Good old trigonometry here, right? We have a right triangle. So this leg will be equal to the magnitude of v times sine of theta, the angle between these two. Okay, so height is magnitude of v times sine theta. Okay, so here's the miraculous fact. The magnitude of the cross product is the area of the parallelogram. Say magnitude of u cross v is the magnitude of u times the magnitude of v times sine theta. Okay, so although much different in character than the dot product, we've derived a very similar formula for the magnitude. Right? So that is to say, remember that u cross v is a vector. So we haven't completely characterized the cross product by this formula, but we've characterized half the information, right? Magnitude, but not yet direction. Okay, whereas in the formula for the dot product, since that's just a scalar, it's completely determined by the cosine of the angle between two vectors. Okay, so what happens now if u and v are parallel? Why did I insist that they were non-parallel here? Yeah,
They don't form a parallelogram.
they don't form a parallelogram. So the area of the parallelogram is 0, right? And this matches with the fact that if u and v are parallel, the angle between them is either 0 or pi, right? They're either pointing in the same direction or pointing in opposite directions. Sine of 0 or pi is 0. Right? So this is consistent with this formula that we just wrote. Okay. Then no parallelogram is formed. And the angle between U and V is 0 or pi, which implies the magnitude of U cross V is equal to 0. So when we look at the dot product of two vectors, if it turns out to be 0, we know that those two vectors must be perpendicular. When we look at the cross product of two vectors in R3, and it turns out to be 0, we know those two vectors must be parallel. Okay. Okay. So let's make a precise characterization of the dot product. This is kind of a loose derivation, but now let us say exactly how to determine the vector U cross V, which includes the direction that it points. Right? I haven't said anything about that yet. I've only talked about the magnitude. Okay, so V and W in R3. Then V cross W is determined as follows. 1. Basically, what we just derived. The magnitude of V cross W is equal to the magnitude of V times the magnitude of W times theta. Theta, the angle between vectors, and this cross product is the 0 vector if and only if V and W are parallel. Okay. What I said at the outset, the cross product of V and W is perpendicular to both V and W. Okay, so determine the magnitude of V cross W, and we've almost determined the direction. We've reduced it to 2 choices. Right? Here's a plane spanned by U and V, my notebook. I have a fixed magnitude, say the length of this marker is the magnitude of V times the magnitude of U as sine theta. So there's 2 options. I either point up or down. Right? How do I determine if I point up or down? The sign of the direction of V cross W is determined by something called the right-hand rule. What is the right-hand rule? Anybody study physics heard of the right-hand rule before? Okay, if not. So here's what we do for the right-hand rule. What we do is we take the first argument of the cross product and point our index finger in that direction. So let's say B points in this direction. Then I take the second argument of my cross product, W, and I point my middle finger in that direction. So let's say W points this way relative to B. That is to say, I'll stand behind V, and if W points this way, I'll point my middle finger this way. If W points the other way relative to B, I'll turn my hand upside down. Then I stick my thumb out, and wherever my thumb points is the direction that the cross product points, right? So if I'm looking down the barrel of V and W points out this way, the cross product goes up. If I'm looking down the barrel of V and W points out the other way, cross product goes down, the direction that my thumb points. Okay? It's a really silly thing that we don't have better language to talk about this, but it has stood the test of time. This is how we determine the cross product. Okay. So let's just write a quick summary of that. Point index in direction of V, middle in direction of W, then thumb points in direction of V cross W. Okay. It might seem weird, but a little practice will normalize it for you. Okay, so let's do some examples. Calculate 3, 1, 2 cross -5, 0, 4. Just take a minute and make that calculation for me. Some pencils down. Maybe let's discuss. It's okay if you haven't finished, but let's talk about it together. What do I do first? Calculate a cross product. Yeah, I'm just gonna use the definition, right? Since I have explicit vectors, probably easiest to just use the definition. Okay, so 3, 1, 2, cross, -5, 0, 4 is determinant of I, J, K. My first input goes to the second row. My second input goes to the third row. Okay. So I times the determinant of this 2 by 2 matrix, right? Which is 1 times 4 minus 0 times 2. Minus J hat. Eliminate the second column and the first row, and I get the 2 by 2 matrix 3, 2, -5, 4. So what do I get here? I get 3 times 4 is 12 minus 2 times -5. We get a -10 minus -10. We get a plus 10. Right? K hat. I eliminate the third column. And what do I get here? The matrix 3, 1, -5, 0. So I get 3 times 0 is 0 minus 1 times -5. In other words, 5. So what I'll do here is just write this back in parenthesis notation. And the reason I do that is because my inputs were in parenthesis notation, although it doesn't really matter. If you prefer IJK notation, that's fine. You could leave it that way. But this is our answer. Okay. Again, just the application of this formula that you should remember. Now, what I'll ask you to do here is take a moment after class sometime to verify that this cross product, verify that 4, -22, 5 is perpendicular to both 3, 1, 2 and -5, 0, 4. Okay, just a sanity check, right? This is something I claim, and I didn't write a proof for you. So at the very least, you should convince yourself that this is true in some cases. Practice true all the time. Okay. So remember, the cross product is what I have been calling a deficient or a defective type of multiplication. It doesn't behave as nicely as multiplication of numbers does. But we sacrifice some things to recover this geometric information and have a notion of how to multiply 2 3-dimensional vectors together and get back a 3-dimensional vector. So here's a corollary. The cross product is what we call anti-commutative. What do I mean by that? I mean that it's almost commutative, except for the fact that when we switch the order, we get a negative sign. Okay? So, proof. The right-hand rule. Okay. Let's say I have V going this way and W going this way. Then V cross W goes up. Right? Now, if I change the order, if I go W first, V still points this way. So the cross product points down. right? I flipped between my two choices. Yeah. Okay, good. So here's a quick example. Let us show that I hat cross j hat is not equal to I hat cross j hat. Okay, so if we succeed in demonstrating this, what that tells us is that, oh boy, the cross product kind of sucks. It's not even associative, right? You can't group terms as you please. It depends on the order of operations that you do things in. So how do we verify this claim? Well, let me give you a hint. Let's consider the right-hand side first of the equation. What are some properties of the cross product? Yeah.
I had cross, they had to say.
That's one thing you can do. We did that before, right? So this equals k, right? Okay. So on the left, I hat cross j hat is equal to I hat cross k hat. Okay. So before I told you that k hat cross I hat is j hat, right? Now knowing that we're anti-commutative, I switch the order of those. So what does that give me here? Negative j hat, right? Because k hat cross I hat is j hat. So when I switch the order, I get a negative sign. Yeah? So this is equal to negative j hat. Good. Now let's go back to the right-hand side. On the right, I hat cross j hat. What's I hat cross I hat? Say again. Yeah, right. Because I hat is parallel to itself, right? The cross product is 0 if and only if the two entries are parallel. Okay, so this is 0 vector cross j hat, which is just the 0 vector. Right? These are not equal. So the cross product is not associative. Okay, so here's some of the bad stuff about the cross product. Let's just say some nice things about it. Oh, and it hurt its feelings too bad. So let's take P, Q, and R, little r, all in R3. And A and B scalars. Then we have the following properties. P hat cross the linear combination A times Q hat plus B times R hat is equal to A times P hat cross Q hat plus B times P hat cross R hat. Okay, I did say, I'm saying two things here. I can distribute a cross product across a vector sum, and I can pull scalars out of a cross product. Two, this same type of operation of distribution and removal, factoring of scalars holds when we take the cross product on the other side. So what's this? A times Q cross P plus B times R cross P. Again, the important thing is that you maintain the order in which you take the cross products. Okay. Switch the order, you have to add in a negative sign. Okay. Okay, so let's do a couple more examples. So I want you to consider 3 points. A, point 1, 0, 1. B, the point 2, 1, negative 1. And C, point 0, 3, 0. Okay, so I'll ask you to determine standard equation of what? Standard equation of a plane containing these points and find the area of the triangle with these vertices. Okay, so I'm being a little kind to you in this problem. If I gave you an arbitrary 3 points, you would have to verify that they're not all collinear to ensure that they span a plane, that there actually is a triangle that has these A, B, and C as vertices. I'm just telling you that for free. You don't have to verify that. If we did want to verify that, how would we do it? That's right on the right track. You would look to see if the displacement vectors were parallel, right? So there's one intermediate step to what you're saying, but that's in the spirit of the correct thing. You would find 2 displacement vectors between 2 pairs of points and then see if they're parallel or not, which we could either do by seeing if we can easily see a scalar multiple, but now we have another way to check the parallelness of 2 vectors, right? We can take their cross product and see if it's 0. Either of those is fine, whichever is easiest. However, in this case, how will we come up with the standard equation of a plane containing these points? What do we need to write the standard equation? Yeah.
2 vectors.
That's the parameterized equation of a plane. 2 vectors which are non-parallel that are parallel to the plane, is what you were saying, right? That's good, but that's the parameterized version of the equation. Yeah. Yeah. Right. So we'll find the displacement vectors between two pairs of these points, and then take the cross product, which will give us what? To get a normal vector, right? To write the standard equation of a plane, we need a normal vector and a point on the plane. So, and we'll find that exactly how you described. We'll take the displacement vectors between A and B and C, or some combination, whichever you prefer, and then take the cross product of those displacement vectors to find a normal vector. Okay. So good. So we need a normal vector and a point on the plane. Well, first of all, let's just pick A. Pick A. That's the point. We'll have lie on the plane. Okay. So to find normal, what do we do? Look at the displacement vectors at displacement. Vectors, let's say V, and I'm just picking two of the displacement vectors that have a common vertex, right? So I'll take V to be the vector that goes from A to C, right? Which if I subtract the point C, subtract from the point C to point A, what do I get? I get -1, 3, -1. And W, I'll let be the displacement vector from A to B, which if I subtract these points, what do I get? I get 1, 1, -2. Yeah. Okay. Then B cross W is our normal, right? So I'll take this determinant. -1, 3, -1, 1, 1, -2. Okay, so what we have here, we take the determinant of this 2 by 2. So we get -6 -1. Oh, sorry, minus -1. Okay. And minus j hat times the determinant of this 2 by 2. So what do we get here? We get 2 minus -1. 1 plus k hat times our final 2 by 2 determinant. -1 times 1 is -1 minus 3. Okay, so all together, what do we get here? We get -5, -3, -4. Okay. So now all we have to do is put our data into the standard equation, right? What's the standard equation? Has coefficients given by what? Say again. So what do the coefficients come from? Yeah, the normal vector, right? Okay, so plane has equation -5 times x minus the x component of the point that I chose, right? So 1 minus 3 times y minus the y component of the point I chose, 0. I'll just leave this as is. Minus 4 times z minus the z component of the point I chose. This isn't an equation. It's equal to 0, right? Okay. Not so bad. Technically, the standard equation has the constant d. So let me multiply everything out and collect terms. Or -5x minus 3y minus 4z plus 9 equals 0 is our standard equation of the plane. Now, how do I compute the area of the triangle that has vertices A, B, and C? Where earlier today did we see an area? Yeah, go ahead.
Is it like half the area of the cross product? Or the magnitude cross product?
Yeah, remember, the magnitude of the cross product is the area of the parallelogram that is spanned by these displacement vectors. If I cut that parallelogram in half, I get a triangle, which was actually your suggestion for how to compute the area in the first place, right? Your suggestion, sorry. Right, so for the area of the triangle, compute 1/2 times the magnitude of B cross W. Okay, so this is just applying our formula for magnitude, right? We get 1/2 the square root of -5 squared plus -3 squared plus -4 squared, which, if we do some arithmetic and simplification, comes out to be 5√2/2. Okay. Yeah.
Since you had vector B and vector W in the order of B cross W originally, like that didn't have to be.
Yeah, that's right. This goes back to, remember, to specify a plane, you need a normal. If we switch the order, the normal would be pointing the other way, but it still specifies the same plane. Good question. Okay, great. So let's do one more example. Good, I think we have just enough time. So now this is finally tying back to our discussion of how to specify a plane, right? We need a normal vector. How do we generate a normal vector? Well, very often using the cross product, right? Has this property of being orthogonal to the vectors that you put into it. Okay, so Here's another example. Let's consider planes. Given by following equations: 1 minus x plus 2 times y minus 1 plus 2 times z minus 1, 0, 2 times x minus 1 minus 3 times y minus 1 plus 4 times z minus 1 0. Let me ask you to then parameterize their line of intersection. Okay, so first and foremost, how do I know that these two planes intersect in a line rather than being parallel and not touching, having no intersection, or specifying the same plane? Great observation. First of all, because of the way this equation is written, we know that they both go through point 1, 1, 1, right? If I plug in 1, 1, 1 here, I get 0. Likewise here, 1, 1, 1 gives me 0. But that means they both go through the same point. So we know that they don't not intersect. Now, how do we know that they're not specifying the same point? Yeah. Yeah, their normal vectors are not parallel, right? That is to say, the coefficients on x, y, and z here are not scalar multiples of the coefficients of x, y, and z down here. No. So where is it? I mean, if I ask you a question this way, it won't be a trick question. I'll give you the opportunity to be like, no, you can't do this. But it's good that we can justify that to ourselves, even though it's given in the problem. Okay. All right, good. So note, as was said, point 1, 1, 1 lies on both planes. Okay. And the normals are the following: 1, 2, 2 for the first plane, and M2, 2, -3, sorry, 4. Okay, now here's the tricky part. We know that these two planes intersect in a line, meaning that that line resides in both planes. So what does this tell us about the normals in relation to the line? Well, this tells us that N1 and N2 are both perpendicular, both normal to the line itself. Okay, so we're given two vectors, N1 and N2, which are perpendicular to some line. We want to parameterize that line, which means we need a vector parallel to the line. How can we use the information that we have to find a vector that's parallel to the line? Yeah.
Cross product.
Yeah. Yeah, we could just take the cross product of N1 and N2, right? Because N1 and N2 are both perpendicular to the line. We take the cross product of N1 and N2, and that will be perpendicular to N1 and N2 and parallel to the line, because the line is perpendicular to both N1 and N2. Okay. To find parallel vector to the line, compute N1 cross N2. Okay. So B N1 cross N2 is equal to the determinant of I, J, K of 1, 2, 2, 2, -3, 4. Since we're almost out of time, I'll let you do this calculation on your own and just tell you what the outcome is. We get 14, 0, -7. So the line has vector equation. X, Y, Z is equal to what? Okay, X naught, Y naught, Z naught. That's a point on the line. What point are you guaranteed on the line? Yeah, 1, 1, 1, because 1, 1, 1 is on both planes, and the line is where the planes intersect. So 1, 1, 1 must be on the line as well. Plus our parameter T times our parallel vector. There you have it. Okay, so that is the conclusion of our review. Next week, we'll start to actually do calculus. And yeah, I'm sorry, 3 o'clock. Right, quiz on Monday, 3 o'clock, 24 hours to do it. Open everything, use whatever resources you like. Just please don't talk to each other about it. Okay, so have a good weekend, and I'll see you Monday.